Okay, hey everyone, welcome back to our CNT lesson, CNT 140 lesson. This portion we're going to be covering Chapter 3, the Structured Cabling Systems, and we'll be highlighting the EIA-568 Structured Cable System. We'll talk about some Avaya and Lucent AT&T Systimax premises distribution systems, the IBM Cabling System, Nordics, and D-Connect, or DEC Connect. What we need to start with is talking about today's structure and cabling systems. They offer the guarantee of a consistent high-performance wiring infrastructure that can support a very wide variety of data and voice communications functions. The structured system is a boon for equipment manufacturers and communication system users because it provides a common, predictable medium for interconnecting high-speed computers and workstations, as well as low-tech voice and fax and medium-speed wide-area networks. Like WAN circuits such as DSL and T1 lines. Now, one structure can support virtually all applications. Well, that's the hopes and dreams of the systems anyway. But it can only be done if the design and installation is done properly, and that's where you come in. And there are many different structured cable systems out there, but the one we're going to talk about is the main player in the ANSI TIA, the EIA standards. It's undergone many revisions over the years, beginning with the -A revision. And the 568 standard has dominated the implementation and development of cabling infrastructure and considerably influenced many associated standards, such as the 802.3 Ethernet standard. The 568A system was created to support. And then we also had the IEEE 802.5 token ring. Now, with the -B revision, known as the 568B, the standard took a multi-phase character rather than try to coordinate the diverse technological progression of structured cabling designers and the copper-fiber dichotomy. The TR-42 committee elected to split the standard into multiple subsections, each with its own standing body and revision process. The result was a trio of standards, B1, B2, and B3. Supporting the overall system design standards, copper cabling components, and fiber cabling components. Respectively, each standard division proceeded independently of the others, although the overall goal remains to revise the overall standard on approximately a 4-year cycle. So now we have the latest -C revision, which is upon us. And a new section called the C.0 has been added. The C.0 section will cover generic cabling information, while the C.1 section will continue to cover the current design standards for commercial building telecom cabling, as well as supporting newly emerging ones. Now, the draft revisions of all 4 sections in C are in various stages of approval process. The end result will be a more comprehensive standard that extends the structured cabling system for several of the latest applications, including the 10 gigabit fiber, copper, and coax. The concept of an orderly system of telecommunications cabling has actually been around for many years. In a way, it was inspired by the hierarchical system of the outside plant cabling from the telephone industry. The concept was, and still is, very simple. From wiring center to central offices, large pair count cables run to outdoor subscriber line interface cabinets where small multi-pair cables interconnect. These smaller cables then run to nearby neighborhoods or business areas where the subscriber lines or the drops are then connected to the individual users. Now, inside the central offices, similar hierarchies of main intermediate distribution frames fan out to the connections to the central switch. Finally, between these wiring centers, a network equivalent of the backbone cables will then interconnect central offices and ultimately the long-distance system, which is the public switch telephone network. Inside multi-tenant and larger commercial buildings, a similar hierarchical system of main intermediate wiring rooms is used to distribute telephone service, first to every company or physical floor or wing, and then to every telephone. This building wire system formed the core concept of modern structured cabling. Now, because data distribution has a very similar topology to telephone distribution, structured cabling was developed to standardize the media and connection systems so that high-speed LAN data could travel the infrastructure. We'll decide several LAN cabling systems in this chapter, or describe several LAN cabling systems in this chapter. These systems define the characteristics of cable connectors, the general wiring schemes, without regard to any of the specific LAN topologies that were described in Chapter 2. And all of them also use some form of twisted pair as their basis. The general purpose of the EIA-568 cabling system will be described, as well as several of the proprietary cabling systems that are in wide use. Many proprietary cabling plans have been offered over the history of LAN wiring technology. Early on, the direction of the LAN cabling was uncertain, and several major equipment vendors devised detailed cabling systems that met the needs of their equipment. Any customer who followed their guidelines could be reasonably assured of a LAN cable plant that would operate well with the vendor's products. And of course, use of a particular vendor's products also frequently implied use of a particular LAN topology. Over time, many LAN technologists have learned that the use of a particular vendor's cabling plan might actually limit the utility of their cable plant for other uses. And in some cases, adherence to a cabling system might significantly increase system cost over the other methods. However, a few cable plans offered wide connectivity to both voice and data. From out of those plans, a universal cabling system finally emerged. The EIA-568, now revised as 568C. Now, it is widely agreed that the flexibility and utility of the standard EIA-568C system offers the best alternative for new installations. The standard can be used in lieu of the proprietary cabling systems with little difference in performance. It can easily support a wide variety of LAN topologies and offers a growth of 100 meg and then beyond. The 568C Commercial Building Telecommunications Wiring Standard describes a generic cabling system that can support many types of LANs. In this section, we're going to cover the hardware and wiring issues presented by the standard, and of course the details of many of the wiring components. So now let's take a look at our cabling options. Okay, the 568C cabling system actually includes 4 types of cable options: unshielded twisted pair, shielded twisted pair, multi-mode, the 5125, and the 62.5/125 optical fiber, and then single mode 50 ohm single ohm fiber. The 50 ohm coax is grandfathered in to our systems. Right. The EIA-568 component categories. The cabling combines, the Category C cabling combines the low cost of modular wiring connections and twisted pair cable with a system of performance classifications and installation procedures. The use of modular connectors and twisted pair wire for LANs was made popular by the availability of an inexpensive existing components that were originally intended for telephone system use. Unfortunately, users soon learned that the cable needed to have specific characteristics, such as minimum number of twists per foot, to work properly. The cable needed to meet certain performance levels that varied with the application, and a cable vendor's rating systems, supplemented by the underwriter laboratory testing, eventually was incorporated into the 568 cabling system. The rating system divides wire and components into numbered categories that are associated with increasing levels of performance needed for LAN operation. 7 numbered categories of 568C cabling are now specified and shown here behind me in the table. Now, although low performance categories 1 and 2 are specifically excluded from consideration in the standard. Now, 2 of the remaining categories, 3 and 4, are officially dropped for new installations, although both may continue to be used for the appropriate purposes of existing locations. Cat 3 can support 10 and 16 MHz networks, such as a traditional Ethernet and token ring. Rarely seen Cat 4 supports up to 20 MHz. Cat 5 has been dropped for new installations and replaced by Cat 5e, which is now the entry level for UTP cabling. Cat 5e supports 100 MHz networks as well as the lower speeds. Cabling devices are often rated by the industry in both bandwidth in megahertz or gigahertz and in throughput or data rate, which is meg or gig per second. Regardless of which number you see, the bandwidth of a component is the limiting parameter. This is because data encoding techniques often obscure the actual cable signaling rate, which is bandwidth limited. For example, the older 10 and 16 meg Ethernet and token ring network required matching cable bandwidth of 10 and 16 megahertz because their signaling structure actually operates at those bandwidths. But 100 meg networks techniques can range from 15 megahertz per pair to 33 megahertz because of the encoding of the data. If a certain multi-pair encoding is used for 100 meg Ethernet, say 100 base T4, it can actually run an older Cat3 cable which is rated to 16 megahertz. However, current day installations should be at category 5E or above and can easily accommodate gig-meg data rates and lower. Cat6 extends operating frequencies to 200 megahertz, tested all the way to 250 and beyond now, and increases operating margins at lower speeds. Components such as jacks and patch panels are also rated by category of performance. Augmented Cat6 has a testing frequency of 625 megahertz and operation to 500 megahertz. The augmented Cat6 corresponds to the ISO IEC 11801 Class E augmented standard. Then there's Cat7. Now Cat7, the newest of the standards, is undergoing considerable development, but is able to support bandwidth of 1200 megahertz, roughly equivalent to the 11801 Class F. The EIA-568 connector standards. The standard 8-pin RJ45 style modular connector are used by the EIA-568C non-traditional connectors, added for Cat7. As we'll talk about those later. You'll see the Cat7 connector. It looks like a shielded connector. It's a little bit different. Okay, 4-pair 24 gauge cabling will be for Cat7. Now the UTP provides the station cable. All 8 wires are connected to the jack. A system of optional punch-down termination blocks and patch panel complete the connection system. The wire connection is straight through, which means that pin 1 and at pin 1 of a cable will correspond to pin 1 at the other end of the cable. Now this is true whether we're talking about a user cord, patch cord, an in-the-wall station cable, whatever. Now this is a departure from the normal 6-wire telephone cords which reverse the connections from end to end. The 568C system allows 2 different color-coded wiring patterns for the specified 8-pin modular connectors. As the figure here shows behind me, we have 2 patterns called the A and the B. Now these are not to be confused with the EIA-568AB standards. Okay, these are our pin patterns, so they're completely different, so don't get those confused. Now the 2 wiring patterns are electrically equivalent, but the positions of pairs 2 and 3 are reversed. Practically this means that the color to pin correspondence varies between the 2 wiring standards. It makes it a little difference. It makes a little difference which one you use as long as you use the same on each end. Now in other words, if you use the 568A pattern at the workstation outlet called the telecommunications outlet, then you must use a matching 568A patch panel or fan-out cable in the telecommunications room. Pairs 2 and 3 just happen to be the 2 pairs used by 10100T Ethernet. So ignoring this wiring convention will cause a connection to fail. Token ring and 4-wire connections, including a T1, will also have a failure. Now many pre-wired components are not marked as to a wiring pattern, particularly non-rated octopus fan-out cables. So be aware of what you're installing. The EIA-568 uses the 568C standards, or I should say the EIA-568 uses. The EIA-568C standard defines many wiring structures that apply to all telecommunications wiring, including traditional telephone system wiring. The hierarchy of these wiring structures we'll talk about in Chapter 14. Although the standard creates a very serviceable telephone wiring system, the real need lies in LAN applications, which are much pickier about transmission characteristics. Now, the portions of the standard that apply particularly to LAN wiring restrict such things as the length of the cable, cross connects, and the characteristics of the cable in installation techniques. If you use the 568C system for a LAN, you may need to restrict the wiring to a particular category, such as Cat5e or 6. And this will place additional requirements on your wiring, such as the maximum cable run, the type of cable, the amount of untwist, and the number of cross connects or punch down points that are acceptable. The benefit to you is that your cabling system will not only support your current LAN requirements, but will likely support future LAN generations. Now, as the figure shows behind me, we have a summary of the characteristics of the 568C cabling. Standard wiring patterns for the plugs, jacks, punch-down blocks, and patch panels are used for the 568C system. So we'll look at chapters 5, 6, and 7 for further details. Now I want to talk about the Avaya, Lucent, AT&T, Systimax, and so on. The Premises Distribution System, or PDS, is a wiring system that bears great similarity to the 568C system. The original PDS system, however, is basically a multi-purpose telecommunications wiring system that can also be used for LANs. In contrast, the 568 UTP system is primarily designed with LANs in mind, but can also be used for telecommunications. The original Systimax PDS system has been updated to reflect all of the TIA standards. Originally, PDS is a comprehensive system that covers telecommunications wiring from the building cable entry through intermediate cable distribution of the wire centers to the telecommunications outlet. It also encompasses campus distribution. PDS uses either UTP or fiber cable. Copper is used for horizontal wiring to the workstations, and fiber is used for vertical wiring between the wiring closets. The copper pair is a 4-pair, 24-gauge cable, while the fiber is 62.5/125 cable. The 8-pin modular connectors are used for copper, and ST connectors are used for the fiber. The basic layout of a telephone-style wiring plan assumes that there will be hierarchical cross-connect points where large pair count cables are terminated and then fanned out into smaller cables or to station cables. The length of the individual runs and the number of cross-connect points are not critical because traditional telephone equipment can run much longer distance than LAN cable. The PDS will use a 110 block as the basic cross-connect component, and then station outlet modules are then use insulation displacement connectors that snap into a modular faceplate. All connectors are normally specified as 8-pin RJ45 style connectors, although the 6-pin RJ11 and 12s are also available. The connector modules are available with markings for data or voice, and the rears of the modules are color-coded to the wires of the 4-pair cable. The Avaya, Lucent, the AT&T color code, and pin mapping are shown here in the table behind me. Now, note that the standard wiring pattern for the PDS 8-pin modular jack is identical to the 568B pattern of the EIA-568 Standard. This is not a coincidence, as the influence of standard telecommunication wiring plans such as PDS carried great influence in the design of the EIA-TIA standards. An earlier Western Electric plan, referred to as distributed inside wire, was a logical precursor to both PDS and the EIA-TIA systems. In the 1980s, the IBM Corporation designed a multi-use cabling system to support the rapid introduction of twisted pair wiring for computer networks. The cabling system uses a unique connector called the data connector, or hermaphroditic connector, and several types of cable are identified by a simple numbering system. The figure 3.3 here in the table, it's also in your book, shows a picture of a data connector, and the table lists the cable types and their characteristics. The cable types designated Type 1 through Type 9 include the STP and UTP cables, as well as combinations of both. The concept behind the IBM Cabling System is that most workstation locations actually need at least one data circuit and one telephone circuit. Both needs could be provided by one cable, such as the Type 2 cable, with shielded pairs for the data and unshielded pairs for the telephone. The cabling system uses a clever genderless connector that eliminates the need for two complementary connector styles, such as a plug and jack of modular wiring. Data connectors simply plug together to make a connection. Now, this requires that the identical style of connectors be used at the cable end, wall plate, and patch panel. The unique data connector was probably designed with token ring in mind, since that has long been IBM's network of choice. It contains a mechanical shorting bar mechanism that can electrically loop back a cable or jack when it's been disconnected. An operation very similar to that of the token ring MSAU port. The IBM Cabling System installations consist of a series of interconnected wiring closets that with star wiring to each workstation location. Now, as we mentioned, either STP or UTP pairs or a combination are contained in each station cable. The STP station pairs are then terminated in a data connector at each end. The data connectors have no genders such as male or female or jack plug arrangement of most cabling systems. These data connectors are mounted in a flush mount plane at the workstation outlet in a patch panel called a distribution panel, which will be at the wiring closet, but are otherwise identical in function to those used on cable ends. The distribution panel typically contains 64 mounting positions for data connectors that terminate the end of the station cables. It is customarily mounted on freestanding 19-inch rails. The distribution panel also contains strain reliefs for the station cables. Also, we have data connector style cables that are used using Type 6 cable. They're used for patch cords in the wiring closet. The connection at the workstation is a cable with a data connector at one end, and at the other end, an appropriate connector for the particular equipment to be connected. By simply terminating the cable with an appropriate connector, the IBM Cabling System can actually support quite a variety of data communications equipment, including coax, twin-X, RS-232, token ring, or Ethernet. In the case of token ring, a 9-pin D-shell connector is the appropriate connector for the workstation. The workstation's token ring interface is 150 ohms, as is the STP station cable, so no matching balun is needed. And for those who are just reading through and aren't sure of a balun is an electrical device that converts between a balanced signal to the two signals working against each other, where ground is irrelevant, and an unbalanced signal, a single signal working against the ground or a pseudoground. A balun can take many forms and may include devices that also transform impedances, but need not do so. Transformer baluns can also be used to connect lines of differing impedance. The origin of the word balun is balanced plus unbalanced. So the workstation's token ring interface is 150 ohms and is the STP station cable. At the wiring closet end, many MSAUs are equipped with data connector ports and use an ordinary data connector patch cable at the workstation. And use an ordinary data connection patch cable. At the workstation location, the telecommunication outlet is composed of a faceplate and a regular data connector, which terminates the station wire. Type 1 wire terminates in a single data connector, while Type 2 wire terminates in one data connector and one telephone jack connector. Both connectors are designed to clip into the faceplate. The IBM system offers two basic styles of faceplates. Type 1 has a single data connector position, while Type 2 also includes a position for the 8-pin RJ45 style connector for telephone use. Conveniently, the Type 1 outlet is used with Type 1 cable, and likewise Type 2 with Type 2 cable. Both faceplates are available in surface mount as well as flush mount options. Now, as the figure here behind me shows, we have a typical workstation outlet for use with Type 2 cable. Other vendors offer data connector outlets in several other connector combinations. The cable and connectors have a matching color code to make wiring simple. However, the cable has a thick insulation and shielding that complicates the termination process in comparison to other types of twisted pair. This is undoubtedly why even the station cables are often terminated directly into a data connector rather than a punch-down arrangement as conventional twisted pair. Cable is available in both plenum and non-plenum ratings and must be placed appropriately. Termination of the data connectors described later on in Chapter 9. The cabling system also includes Type 5 fiber optic cable. The fiber and connectors are basically the same as other wiring methods. Termination and descriptions of fiber optic cable are described elsewhere. Several other variations of IBM cabling systems might be found, the most common being Type 3, 6, and 9 cable. Type 6 and 9 are 26 gauge non-plenum and plenum versions of Type 1 cable. Type 3 is 105 ohm, 24 gauge unshielded, twisted 4-pair cable that meets IBM specifications. It is available in plenum and non-plenum insulation and is similar but not identical to Cat 3 cable. When Type 3 wire is used as station cable, a special adapter cable called a media filter must be used to match the 105 ohm cable to a 150 ohm device interface, such as token ring interfaces. Some newer token ring interfaces also have a 105 ohm modular jack, which eliminates the need for the media filter. Similar media filters may be used with 100 ohm Cat 4, 3, 4, and 5 cable. Now please note, older media filters may support only 4 meg token ring and will fail when used with 16 meg rings. The IBM Cabling System provides some important advantages in mixed application environments that may use coax, twinax, and twisted pair terminations. The cable has been designed to support all these types of signals using the proper adapters of impedance, matching balance. However, in a LAN-only environment, such as token ring, the function may all be satisfactorily accomplished by the 568C system at a much lower cost. In fact, most estimates place the cost of an IBM cabling system installation at 2 to 3 times of a standard 568C installation. Now, many other vendors have developed proprietary wiring patterns for cabling of data and voice. Most of these plans support specific features of that manufacturer's equipment and are not general purpose at all. Others incorporate variations of the cabling systems that we previously talked about. There are 2 other systems are widely used, and they do deserve to be mentioned. The Nordics /CDT and IBDN. Now, another variant of twisted pair wiring is the Integrated Building Distribution System. Originally put forth by Northern Telecom, often referred to as Nortel, and the IBDN components are now marked by Nordics/CDT, a Nortel spinoff. Now, this system is quite similar to the Avaya, Lucent, and AT&T PDS and supports telecommunication wiring. As we saw with the PDS, data networks can run over these systems, but the distance limitations and other installation practices must be observed. The IBDN uses the common system of modular connectors with cross connects based around the BIX block. Now, the IBDN also contains fiber components, as does the PDS. And while the IBDN system is not specifically designed to match the 568C requirements, it will allow common types of network connections if the distance limitations of the network are not exceeded. When used in accordance with the guidelines in the standard, an IBDN installation can be said to be a 568C compliant. All the modular connectors, jacks, cable, and color codes of AT&T PDS are common for IBDN. The interconnection component, of course, is the BIX block, rather than the 110 block. In general, the IBDN system is compatible with the 568 structured wiring, and its components may be substituted where they meet the standard performance specifications. please refer to the PDS section in this chapter in the Bixblock section of Chapter 7 if you would like more information on that. The DEC Connect, created by Digital Equipment Corporation, the DEC Connect system supports 4 communication technologies in an attempt to provide a global wiring system. Now the 4 technologies are voice, video, low-speed data, and network. And the DEC's approach uses 5 different types of cable that are run individually to the DEC faceplate at the communication outlet. The 5 cable types are listed here behind me, along with their preferred connectors. The complete DEC system is rarely used because of its separable cable technologies and its unusual data connector. If you must run a different cable type to each workstation, you might as well keep each technology totally separate. The only advantage the DEC system offers to the mixed media user is a common faceplate mounting for the connectors. The system uses a unique MMJ connector with an offset locking tab and keyway, which is shown here behind me. Now, unlike a normal key jack with an extra keyway at the side of the opening, the MMJ will not accept a non-MMJ plug at all. It is totally incompatible with all other modular devices, including connectors, jacks, and adapters, fan-out cables, patch panels, and the test equipment. Special MMJ devices must be used, or an adapter cable must be fashioned. The first M may stand for maddening because of the shortcomings of the DE Connect system, or DEC Connect system. The DEC Connect wiring is primarily used to connect legacy DEC asynchronous computer terminals using a variant of RS-232 and 422 wiring. These async terminals use an MMJ connector for the interface. The DEC Connect system specifies a clever symmetrical wiring pattern for the data connector that avoids the failure that would result from reversing the order of pin wiring, which is a common error. Ironically, the most frequent source of this type of error would come from the use of standard telephone cables that flip pins from end to end. These are the very cables that will not plug in to MMJ outlets. And that covers the Chapter 3 Structured Cabling System chapter for us today. Be sure to come on back for our Chapter 4, as this lesson will be Chapters 3 and 4. If you have review questions due yet in your book, go ahead and knock those out, and then come on back here and we'll complete the next chapter. See you.